In this unit, we're going to learn how to count. And that may seem like a trivial task because we've been counting for the majority of our lives, but there are lots of different counting methods, especially when counting can become really difficult to do manually. So we know we can count on our fingers, and we've only got 10 of them, so it would be helpful if we had some methods that would allow us to count. And combinatorics is this fancy word that just means it's the study of counting methods. And there are many, many different counting methods. There are entire classes on this. And in this video, I just want to motivate counting via what we call probability. Probability is something we're constantly trying to assess. If we're in game development, we have random chances that certain things will happen in order to make games more interesting. Otherwise, if things always happen the same way, we tend to get bored. Probability is also very useful in measuring how likely, for example, servers are to fail. Lots of applications of this. So in this video, we're just going to briefly motivate these two principles and see how combinatorics will allow us to formulate likelihood statements. So probability, well, what is it? Well, it's a measure of the relative frequency. Okay, so that's the more mathematical term, but we often just say likelihood. Relative frequency is really describing something that is expected to happen when the same trial is performed repeatedly. So you can think about it as, out of all the possible outcomes, how many different ways or how many different times will this particular event occur? We're going to come back to this. We're going to come up with a better definition for this that will allow us to mathematize it. But let's take a look at a couple of ways that we could just introduce counting. So we're all familiar with some standard events that maybe we study in probability, and those are coin tosses and die rolls. And they're not very interesting by themselves because we often don't toss coins and we often don't roll dice, but it helps to motivate the idea because other events are very similar to these two types of actions. So suppose we toss a coin that has two equally likely outcomes. Okay, equally likely, first of all, is a common phrase that we use to describe that really if you toss a coin, you're just as likely to get heads as you are tails. Well, if you only toss a coin once, you're only going to get a head or you're only going to get a tail, but the idea here is that you can bet your money on either side and there's a 50-50 chance that you're going to get the outcome that you want. If we repeat this event 2 times, what are the possible outcomes? Well, we could start maybe rattling those off. We could say, well, you could get heads 2 times in a row. And by the way, this is what heads often looks like when we imagine a coin. We have heads and we have what's called tails. And we could kind of start thinking about this. We could say, well, you could get 2 tails, you could get 2 heads. But it's nice to have some sort of visual way of representing this. So what I'll do is I'll build a little tree diagram, and a tree diagram just helps me keep track of the possibilities. So first of all, I'll take a look at the possible outcomes for toss number 1. Okay, so for toss number 1, I'll draw this little diagram, I'll draw this little root of this tree, and for toss 1, I know that I could get heads or I can get tails. Okay, so those are my 2 possible outcomes for that first toss. Now, toss 2 has the same possibilities, right? Just because I toss a head on toss 1 doesn't mean that I'm any less likely to get another head on toss 2, but I want to keep track of the sequence. So rather than just to say heads and tails again, what I'll do is construct a new branch for toss 2, contingent upon what happened in toss 1. So if toss 1 resulted in heads, then for toss 2 I could still get heads or I can get tails. If I tossed a tails on toss 1, then once again I could get heads or I can get tails for toss 2. And what this nice little tree diagram has allowed me to do is now I can follow the tree from the root to any end branch and figure out what that combination is. So here I have if toss 1 is head and toss 2 is head, then I have the sequence heads, heads. There are lots of different ways you can express that. You can just say HH. You can even say, as an ordered pair, H comma H, like that. It means first trial, second trial. We'll just go ahead and stick with HH for now, for simplicity. Then, again, if I follow the branch from the root, I can go heads, tails. I could go tails, heads. Or I could go tails, tails. Now that establishes that there are 4 possible outcomes. And they're all equally likely because at each juncture, whether I get a head or a tail, there's a 50-50 chance. And so in this situation, we can certainly say that these are equally likely. So we already have a counting method available. This is by building what we call a tree diagram. It's called a tree diagram because it resembles the branches of a tree, of course. All right. Now, how do we begin understanding probabilities of certain outcomes? Well, in what we call classical probability, if you can actually count the number of possible outcomes and the number of ways the thing that you want to happen can happen, then you can formulate this relative frequency. Relative means you take one frequency, you relate it to another via division. The probability of some event, E. By the way, this is a set. That's why we're using capital letters, is the number of ways the event can happen. And we know that the size of a set, we denote using kind of the absolute value sign. That's the magnitude of that set, divided by the total number of possible outcomes in S. And S is what we call the sample space. Again, this is also a set. This is the set of all possible outcomes. And when we divide those, we get a sense of, well, what's the likelihood that if I were to repeatedly perform this experiment, that what would be the percentage of time that E happened? Well, let's apply this back to our coin toss example. What is the probability that we get exactly one head in 2 tosses? So we'll start with the sample space. Well, what are the possible outcomes? We go back up to our tree diagram. We had heads, 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 tails, tails, heads, and tails, tails. Okay, so there's our set. That's the set of possible outcomes. Again, whether we choose to represent the elements of that set as ordered pairs or just these 2 letters smashed together indicating the sequence of outcomes, we see that there are 4 possible outcomes. So the size of S is 4 elements large. Each element represents one sequence of 2 tosses. Now, what's the event that we want? Well, we want to get exactly one head. So what I'll do is I'll look at my sample space and I'll only pick out the ones that represent the outcome that I want. Exactly one head means not 2 heads, it means one head. Well, we see that that's here and here. I get exactly one head. Remember, these are 2 distinct outcomes. One is where the head occurred first and then a tail, and the second is where a tail occurred first and then a head. And so I will write these in my desired event. And we see that the size of the event space, we call that the event space, or the set of events that I want to occur, there are 2 ways that can happen. Now, since these are equally likely, the probability that event E happens, if this looks like function notation, it's because it is. It's what is the probability of that event? Well, it's the number of ways that event can happen divided by the number of things that can happen, and that's 2 out of 4, which we could leave as a fraction, but typically we express them as a decimal. Now, every probability, by the way, is going to be between 0 and 1. If you ever heard somebody say, I'm 110% sure, well, as a mathematician, I have to kind of roll my eyes a little bit because 1 represents 100%, and that means guaranteed. right? That means guaranteed. It's going to happen. There's no uncertainty. 0% chance is also kind of means there's no uncertainty, but that means that there's a 0% chance that it will happen. So it will not happen, right? It will not happen. So there's no uncertainty at 0% and there's no uncertainty at 100%, but typically outcomes and their likelihoods are somewhere between 0 and 1. So you can't have a negative probability, you can't have a probability bigger than 1 or 100%. Makes sense, right? Because if I just said, what's the likelihood that something happens in the sample space? Well, something happening in the sample space here means that one of the 4 things happens, and that's a 4 out of 4 possibility. You can't have 6 things happen out of only 4 possible outcomes. So as far as the meaning of this, right, because the meaning is important, if I toss a coin twice, and I do that many times, what does many mean? Well, in theory, that means infinitely many. At the limit, as the number of times I repeat this approaches infinity, if I toss a coin twice and I do that many times, about 50% of all those 2-toss trials had exactly 1 head. All right, so you could toss a coin twice and get both tails, and you could toss a coin twice and get 2 heads, and you're like, well, there's 0% of the time within those two toss trials that I get exactly 1 head. How can this probability be right? I got 0%, but the theoretical probability is 50%. And that's exactly what this is. It's a theoretical probability that if you kept doing that 2-toss trial over and over and over again, then and counted the number of times out of those that you got exactly 1 head, it would be about 50%. How many times is enough? You know, if you repeated a 2-toss experiment 100 times, you'd probably get pretty close to 50% of those having exactly 1 head. But even then, it might not be exactly 50%. And that's one of the, I think, confusing things about probability is, well, things either do happen or they don't. But probability is a measure of the relative frequency that something will happen if you do it many, many times. Okay. Well, what's the probability? Here's just another statement that we get at least 1 head in 2 tosses. And this is a common thing because maybe we're going to be playing a game where all we need is just to get 1 head and we'll win. Or maybe in that same game we get 2 heads and we still win. And so at least 1, it's a common probability statement, means 1 or more. All right, so the sample space is the same, right? It's the same sample space as above. We already know that there are 4 possible outcomes, and let's build the event space. Okay, so which of these 4 outcomes result in getting 1 or more heads? Well, it's still the HT and the TH. There's exactly 1 head there. But then also heads has at least 1, right? In example 2, we're looking at getting just 1 head, but now we're saying, well, we're good with 1 or more. And the only thing that changes here is that now there's a higher likelihood that we win this game because now 3 out of the 4 possible outcomes result in the event that we want. And so the probability of getting at least 1 head is the number of ways that can happen divided by the size of the sample space. So you see, again, what we're doing here is we're counting things, and in some senses, some of what we're counting is a little bit primitive, but we also have to have some way of some framework by which we can think about it. And our little tree diagram did a lot of that work for us. Well, what if we extended this example and we said, well, what about getting exactly 2 heads in 3 coin tosses? Okay, well, that's a little bit trickier because if I did try to count this, first of all, well, I could say, the first two tosses could be heads and then a tail. It could be the first and the last toss could both be heads, and that would be a win. Or it could be the last two tosses that could be a head. Well, I think what makes the most sense here is to take our diagram, look at the outcomes for toss 1 and toss 2, but extend our table a little bit further, our diagram a little bit further, and also take into account the sequence of events with toss 3. So here I'll start with the root. Toss 1 can be a head or it can be a tail. If toss 1 was a head, toss 2 could be a head or a tail. So this is looking a lot like our initial example with just 2 coin tosses, but the difference here is we're going to build this tree diagram out even further. We're going to say, well, if we got a head on the first toss and a head on the second toss, toss 3 could still be a head or a tail with equally likely chances. If we got a head and then a tail, we could get heads or tails. If we got tails, heads, we could get heads or tails. If we got tails, tails, we could get heads or tails. Now maybe at this point you're already starting to see that this technique is great as long as you're probably within 3 or fewer tosses, but if we added a 4th toss, this tree just kind of keeps expanding out actually pretty rapidly, right? We have 2 possible outcomes, 4 possible outcomes for toss 2, and now we have 1, 2, 3, 4, 5, 6, 7, 8. So the number of possibilities doubles every time we include a new toss. So if we had toss 4, we'd have 16 possible outcomes. Now, our sample space is going to consist of all of those possible outcomes, right? So heads, heads, heads. Again, we could write this as an ordered triple, heads, comma, heads, comma, heads. But we'll just choose to write it like this. Then we have heads, heads, tails. Then we have heads, tails, heads. Heads, tails, tails. So that takes care of the first 4. Now, tails, heads, heads. Then we have tails, heads, tails. Then we have tails, tails, heads. And finally, tails, tails, tails. So we see that there are 8 possible outcomes in there. And that's also indicated by the number of branches that we have at the end of our tree. And now we just need to figure out which of those result in exactly 2 heads. Well, we've already started to list them out here, but we see that HHT, HTH, and THH both have, or all 3 of those have exactly 2 heads. No more, no less. And so the size of our event space is 3. And so the probability of that event is going to be the number of ways it can happen divided by the number of possible ways. And 1/8 is 0.125. I think this is going to be 0.375. Or if you wanted to express it or think about it as a percentage, there's a 37.5% chance. So again, if you were to toss a coin 3 times, and then toss it 3 times again, and then toss it 3 times again, and then just repeatedly do that, and you looked at or counted how many of those 3 toss sequences resulted in exactly 2 heads, if you did it many times, enough times, you'd see that it would be around 37.5%. Well, we could easily formulate these statements into not dealing with coin tosses, but let's say that instead of a coin, what we're looking at is a server, and we want to know, okay, what's the likelihood that if we have a bunch of servers that maybe all contain the same data, like if you think about big companies, they have multiple servers all carrying similar or the same amount of data in case one crashes. that there's a backup server to be able to work with. You could think about, well, either the server fails or it doesn't fail, in place of thinking about the outcomes of a coin toss as either heads or tails. Now, would the probability of failure be the same as the probability of non-failure? That's unlikely, right? Hopefully you get a server that has a very small chance of failure, but the same kind of logic would pan out. You could think of H as maybe the server doesn't fail. So for 3 servers, doesn't fail, doesn't fail, doesn't fail, all the way down to does fail, does fail, does fail. Well, instead of tosses, these could be server status. And by using coins and dice, it just makes things a little bit more intuitive at first. Okay, one more example. You roll a fair 6-sided die twice. What is the probability you roll 2 even numbers? Okay, so fair 6-sided die just means every, once again, outcome has an equally likely chance of coming up. And a single die will have the either 1 black dot, 2 black dots, all the way up to possibly 6 black dots. Now, how do we begin assessing what the possible outcomes are? Because we want to look at all of the outcomes and we want to see, well, what's the likelihood that they both are even? So right now, with just implementing counting techniques, we might again think about each roll and what's the outcome of each roll. Okay, so roll 1 could be a 1 or a 2 or a 3, a 4, a 5, or a 6. Now, if on roll 1 I got a 1, on roll 2 I could also get another 1, right? If I roll those 2 dice, it could be that I get 1, 1, one black dot facing up on each of those two dice that I rolled. And of course, every roll for roll 1 is going to have 6 possibilities for roll 2. All right, so what I'm going to do here is just put a little dot, dot, dot there, because roll 2 could be 1, 2, 3, 4, 5, or 6, regardless of what roll 1 was. So each of these branches is going to have 6 branches on roll 2, and that's going to be 36 separate outcomes that I need to draw out. So maybe the tree diagram is not the best visual approach here, and we will learn more optimal techniques for doing this without necessarily having to draw it out. But here's another way we could do it. We could actually draw a little table, and we could say that roll 1 will be represented along the rows 1 through 6. And roll 2's outcome will be represented along the columns. And every single intersection of a row and a column indicates the combination of outcomes for roll 1 and roll 2. Okay, so there we go. All right, good enough here. And so, for example, in this cell right here, we get a 1 and a 1 for both of those 2 die rolls. Here we get a 1 for die roll 1, a 2 for die roll 2. You can really see that this first row is just representing this first section of the tree diagram, and then a 1, 3, a 1, 4, a 1, 5, and a 1, 6. Now, what we want to ask is, first of all, we see that there are 36 possibilities. There are 36 cells in this table. And that tells me that the sample space in size is 6 times 6 equals 36 possible outcomes. I'm not going to list them all out, right? It doesn't make sense to list them all out because the sample space is too large to want to write down 36 different sequences. Now, I need to figure out how many ways my event can happen. And again, I don't want to list out all those possibilities because there's probably going to be a lot of them. But what I do know is that in order for both rolls to be even, that means roll 1 can be a 2, a 4, or a 6. So I know that row 1, row 3, and row 5 are not going to lead me to the event that I want. Also, roll 2 will have to be either a 2, a 4, or a 6. And that means I could get a 2-2, a 2-4, a 2-6, a 4-2, a 4-4, or a 4-6, and a 6-2, 6-4, 6-6. Now be honest, did you think that it would be 50%? Well, in fact, there are only 9 possible outcomes in which both of those numbers are going to be even. Now, it's also going to be true for 2 odds, because in reality, it's more likely that we get a mixture of 1 even and 1 odd. And so having only 9 of those 36 possibilities both being even just means that it's not equally likely that we get 2 evens as opposed to just getting 1 even. If I toss the roll the die just once, getting a 2, a 4, or a 6 is as likely as getting a 1 or a 3 or 5. It's when we incorporate that second roll that now we could have all those mixtures of even, 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 odd, odd, even, odd, odd. And so this comes out to 1/4 or 0.25. Again, rarely do we list out the percentages unless we're trying to communicate this data to somebody. But 0.25 is the way we usually write it, because now if we're going to be doing other computations with it, we don't perform computations on percentages. We always work with decimals or fractions. And this video, I've just aimed to kind of provide some frameworks for how we can count and why we count, and then how that can lead to a better understanding of likelihoods of outcomes.